Good morning, it's Jeremy. It's Friday, September the 22nd, and I'm just looking at a picture of the PWM signal given off by the Varioprop 6 transmitter. In the last video, we looked at the Varioprop system for remote control of model airplanes, and the signal we captured off air. The carrier here is 27.145 megahertz. And the signal typically is a repeating pattern of 4 bursts. The first burst will be pulse width modulated for the rudder control, and the second burst is for the elevator control, and the third burst is for the speed control. The 4 pulses repeat about 11.6 to 11.7 milliseconds. Like I say, each burst consists of carrier of 27.145 megahertz in the CB band. So what I did is I simulated that in Scicos. So here's the Scicos simulation. So to do that, basically we're going to have I'm going to use a sine signal for my control signal. So basically it'll go up and down. When it goes up, that'll be, let's say, the rudder control going, let's say, to starboard, and when it goes down, it'll be the rudder control going to port. So it'll be a linear function here. And the sawtooth generator is what we use to generate the pulse width modulation, and we compare the sawtooth against the sine. We subtract the two, and then we take the signum. The signum is, if the signal is greater than 0, it's a 1, and if it's less than 0, it's a 0. So let's see what that looks like. So when we run the simulation, here's the sawtooth. Now I set the sawtooth up for the 11.6 milliseconds, so that works out to a frequency of about 86 hertz. So there's the sawtooth, and there's my control voltage, and there's the pulse width modulation signal. So you can see when the control voltage is most positive, that would be the, let's say, control signal, like fully starboard, then you get the maximum pulse width, and then when it's minimum, you get the minimum pulse width. I've set this up for about 90% pulse width during the 11.6 milliseconds and about 10% minimum. You adjust the voltage on here to get the plus or minus 90% and 10%. If you make this, let's say, positive voltage less, then this thing will be a little bit more than 10%. So you can play with the sawtooth to get the absolute settings for the pulse width modulation. Now that's just the baseband. If we want to look at the RF, so that's the RF. That's the pulse width modulation on the baseband, and then you multiply that by the carrier, and here's what we get. I'm only simulating one pulse, let's say the rudder control. So when the control is hard over, you get the widest burst of carrier, and when the control is hard over the other side, you get the minimum. So that's basically a quick overview of how you could simulate pulse width modulation. Just another note on pulse width modulation. I think it's a very, very interesting modulation technique. It's kind of a mixture of analog and digital. It's digital in the sense that the noise, let's say you transmit the signal, you can add noise to this, and it doesn't matter. On the receive end, you just amplify it and clip it. You get rid of the noise, and it's analog in the sense that the width of the pulse here is directly proportional to the control signal. So it's analog in that way, and then digital in the sense that it's either there or not there, and you can get rid of the noise. So it's a very good modulation technique. It's used for motor speed control, and it's also used for let's say Class D amplification for amplifiers.